Welcome to the class. Dear students, today we are going to see bromination of nitrobenzene. So, when I say bromination of nitrobenzene, what do I intend to put forth is that what is the product we get on bromination of nitrobenzene when we brominate nitrobenzene. The second question that I intend to answer is, or that I intend to address is, what is the mechanism of reaction? If such and such product is formed, then what is the mechanism of reaction? So there are two questions that I intend to put forth. The first question is, what is the product? Number two, if such a product is formed, then what is the mechanism of reaction? To know the answers to these questions, we have to see the structure of nitrobenzene, and also we have to introspect the effect of nitro group on the electron density of the benzene ring. So let us look at that point, the bromination of nitrobenzene. This is the nitro group, and when the nitro group is attached to benzene, is attached to the phenyl group, what happens? The nitrogen, it gives its lone pair to get attached to this benzene ring or to this aromatic ring. So when it gives its lone pair of electron to the benzene ring, it acquires a positive charge. Now look at this. These two are electronegative atoms which are attached to nitrogen. Nitrogen itself is an electronegative atom. So being electronegative, there is strain in this bonds, correct? There is a particular strain, a special strain here in this bond. The oxygen wants to take the pair of electron towards it, but the nitrogen, the positive charge on nitrogen doesn't allow the oxygen to take so. It holds the electron pair towards itself, correct? Another way the nitrogen exerts its action is to pull this electron pair. It prefers to pull electron pair from this carbon, which is electropositive in nature, rather than oxygen. It won't go for a fight with oxygen because they are both electronegative. So rather to ask electron pair from oxygen, it would ask electron pair from carbon, because carbon is electropositive in nature and carbon would donate, right? So this electron pair jumps here. When this electron pair jumps here, the positive charge of nitrogen, we get rid of the positive charge of nitrogen, and the requirement of nitrogen to hold on to this pair also goes. So this electron pair now goes to oxygen. So that is what we get in the second canonical form when nitro group is attached to benzene. In the second canonical form, we have seen that this pair of electron, it has gone to nitrogen, and here which there was a pair of electron, it has gone to oxygen. So this is the second form that we have achieved. In donating this pair of electron to nitrogen, this carbon is not at loss, right? See, this carbon electron is still here. It is this carbon's electron which was given to nitrogen. You can say that the double bond was just flipped. Okay, it was just flipped. Okay, so here the double bond gets flipped, so there is no loss for this carbon. The electron of this carbon is still with it. The loss is with this carbon because it is this carbon's electron that has been donated to nitrogen. So the positive charge now comes here. Okay, now what would happen? Now this carbon, it would, to negate its positive charge here, it would attract the electron pair from adjacent carbon atom. So when it attracts the electron from the adjacent carbon atom, yes, the electron pair comes to this carbon, it comes here. In doing so, this carbon is not at loss because this carbon electron is still there here, right? The loss is with this carbon because the double bond was just flipped. Okay, so the positive charge comes in this. So that leads to the third canonical form. The fourth canonical form, what happens? Now this carbon, to negate its positive charge, this carbon attracts its electron. So this electron pair comes here and the positive charge now rests on this carbon. So that is the fourth canonical form. Now look at this carbon. What option does it have? Which is the adjacent double bond? This is the adjacent double bond, right? So it pulls the double bond back into the system, into the benzene ring. When it pulls that electron back, nitrogen gets positively charged, so it will take the electron pair that it has given to oxygen, so the electron pair is back to nitrogen. Right? So now what happens, there is a one complete round that has taken place. This double bond which was initially here has come now here. So the benzene has made one full round, right? It has one full round. So the canonical forms or the resonating forms of benzenes are of nitrobenzene is finished. So how many structures are possible? 1, 2, 3, 4, 5. So we draw the hybrid. The combination of all these structures is called the hybrid structure. So we draw the hybrid structure. In the hybrid structure, we have seen what is particularly more important is that positive charge is on ortho, para and ortho position. Right? So altogether there is a decrease in the electron density, that is right, and specifically the electron density has decreased from ortho, para and ortho position. So that is what is shown here in the resonating structure. Here sometimes this bond is formed and sometimes it is broken. In 2 of the structures there was no bond. In 3 of the structure there was double bond. So that is what I have showed in dash. This also indicates the same. So now this side is negative and this side is positive. That is the phenyl side is positive. So what do we infer? The inference that we have is that nitro group is electron withdrawing group. It withdraws electron from phenyl ring towards itself. By withdrawing electron towards itself, benzene rings electron density is decreased. Benzene rings electron density is decreased. There is a decrease in the electron density of the benzene ring, specifically at ortho and para positions. Electron density has decreased overall, but specifically speaking it has decreased in the ortho and para position. Now if in such a state, if an electrophile, I introduce an electrophile, at which positions it would attack? Yes, it would attack regions of relatively higher electron density. Which are the region of relatively higher electron density? That is, it will attack at the meta position, because meta position is the only region which has a higher electron density. So the product of this reaction, the answer of the first question is that the product of the reaction formed is metabromo nitrobenzene. Why metabromo nitrobenzene? Because the bromine will attack, the Br plus will attack region of relatively higher electron density. There is no electron density at ortho and para position. I mean there is less. Comparatively there is more higher electron density at the meta position. So bromine definitely would go for attack at the meta position. So you get metabromo nitrobenzene. That is the answer for our first question. Now the second question was, to remind you, the second question was, what will be the mechanism of the reaction? If such is the case, then what is the mechanism of the reaction? See, there is one hydrogen here. We do not forget that, right? Already an electron pair has been taken. Correct? Look at this. Already an electron pair has been taken. It has created a positive environment in the benzene ring, which is not so stable, right? And again an electron pair is getting attacked, and that electron pair is given to bromine. Okay, it will lead to more instability. It will lead to higher electron, higher positive charge in the benzene ring. So that would be very short-lived. That such a system would be very short-lived. Yes, it gives electron pair to bromine, but only for a short time. Okay, that would be very short-lived. What happens is an H is going from here, right? It gets rid of the H and this electron pair is introduced back. Okay, so that further deficiency of electron doesn't take place in the benzene ring. So it gives the electron pair back and H plus goes out of the system. So what has happened here? What has happened? One electrophile like bromine has substituted another electrophile in the aromatic ring. One electrophile has substituted another electrophile in the aromatic ring. The mechanism of this reaction is electrophilic aromatic substitution reaction. That is the answer for the second question. The mechanism of the reaction is electrophilic aromatic substitution reaction. Now we know the product that is formed, we already answered that. We also know the mechanism by which that product is formed. Let us now look at the reaction. So what happens in bromination of nitrobenzene? Let us see that first and then we will explain the reaction. So we take nitrobenzene, okay, and we take bromine, correct, Br2. We take an acid catalyst, Lewis acid catalyst, FeBr3, and the product that is formed is meta-nitro, we already know, meta-bromo nitrobenzene. We already know this, correct? There is no doubt about it, HBr, fine. Now, what I want to mention here, the special thing that I want to mention here is that Br2, right? Br2 is actually a, what is it? It's a non-polar covalent compound. It's non-polar. It doesn't have any charge. Does it have any charge? No. The shared pair is, the pair of electron is equally shared between the two bromine. Equally shared. And either of the two bromine, they are both neutral. They don't have any charges. They are completely non-polar. But when they come close to electron-rich benzene ring, if this side comes close to the electron-rich benzene ring, what happens? The electron cloud shifts to this bromine, correct? In that case, this bromine would develop a positive charge and this bromine would develop a negative charge. So it is bound to break. Adding to the fire, adding as a fuel, okay, acting as a fuel is the catalyst, the Lewis acid catalyst. What it does, it is an electrophile. Okay, FeBr3, it has got empty d orbitals. It has got empty d orbital. Fine. And this empty d orbital, what it does, it has space for accepting pair of electron. It has vacancy for accepting the pair of electron, FeBr3. So it acts as an electrophile. So adding, as it also attracts Br minus. So that adapts to the fire. Because benzene attracts Br plus and FeBr3 attracts Br minus, the splitting, the cleavage is bound to take place. The heterolytic cleavage of the Br bond is bound to take place. One Br would become positive, the other would become negative. And it will be the positive Br that will act as a electrophile and attack the meta position, resulting in the meta-bromo nitrobenzene. Dear students, that sums up the reaction. Now let us see the mechanism. So the mechanism, as we discussed, is electrophilic aromatic substitution reaction. Electrophilic aromatic substitution reaction, we have already taken classes for this. Electrophilic aromatic substitution has 3 steps. Step number 1, formation of electrophil. So let us see how electrophil forms in this case. And let us understand what happens. So our acid catalyst is Lewis acid catalyst. Lewis acid catalyst is any substance that can accept a pair of electron. FeBr3 accepts a pair of electron. That's why it's called the Lewis acid catalyst. Why? Because I will tell that this is, of course, Br2. What happens? FeBr4 minus and Br plus. So we got the electrophil. To understand why Fe or ion takes a pair of electron, we have to look at the atomic number of Fe. The Fe's atomic number is 26. In FeBr3, it exists as Fe3 plus. Fe exists as, Fe is in ionic form, right? So Fe exists as 3 plus. So if Fe exists as in this ionic form, what would be the number of electron? This would be minus 3, right? Because 3 electrons are lost. So that would be 23. So let us now go for the electronic configuration of Fe3 plus. That would be 1s2, 2s2, 2p6, 3s2, 3p6, right, and 3d5. Am I right? There is 4s0 that comes above here, but in Fe3 plus 2 electrons have been taken from 4s orbital and 1 electron has been taken from d orbital. So no need to write 4s0, just go for 3d5. So now you can see whether it is 23 or not. 4 plus 6 10, 12, 12 plus 6 18, and 18 plus 5 23. Let us now draw it. We will come to know the status. This is 1s2, this is 2s2. Let us go for 2p6. So this is 2p6, 3s2, 3s2, 3p6. So 3p6 also. And what about 3d5? Let's go for 3d5 and see. 1, 2, 3, 4, 5. So this is the 3d5 orbital of Fe3 plus. It is vacant. The d orbital is vacant. The 3d orbital is vacant. Right? Each can accept one electron. So the 3d orbital is vacant. So it can accept pair of electron. Correct? It can accept 6 electrons like this. Fe can bind to 6 electrons as in hemoglobin. So now you can see the vacant d orbital, not completely vacant but still vacant d orbital, vacancy is there, correct? So it acts as an electrophile, and that is why Fe accepts the pair of electron and becomes FeBr4 minus. I hope you understood why Fe accepts the pair of electron and acts as Lewis acid catalyst. So that is coming back to our point. We have now formed the electrophile. The electrophile would not sit idle. In step 2, it will go for the attack. Attack of electrophile. Attack of electrophile. What would happen? Our Br plus would attack what? Yes, nitrobenzene, and we know the correct structure of nitrobenzene, which is like this. The original structure is the resonance hybrid structure and it is looking like this, right? Everything here is negative because it is electron withdrawing. Here it is positive. Ortho and para positions are positive. So of course Br would attack meta positions. The product would be like this, right? And positive. H has Br. H has not gone, right? Positive charge has increased. Right, so this is the negative sign here and positive sign here. So this is the situation now. This is very short-lived carbocation, very short-lived carbocation because it is very unstable. So this is the step 2 where attack of electrophile takes place at region of higher electron density, which is the meta position here. And now this increase of positive charge has made the ring very unstable, and this ring carbocation is very, very unstable. It is very short-lived. In the step number 3, what would happen? It would reclaim its electron pair but from proton. Step number 3, elimination of proton. Elimination of proton. What would happen here? I am not rubbing this. What would happen here? Because this is very unstable, this pair of electron, it goes. Oh, sorry. This proton, it goes. And this electron pair is retained back into the system. When it is retained back into the system, you get the nitrobenzene. Sorry, metabromo-nitrobenzene. Metabromo-nitrobenzene. So that is the 3 steps. These are the 3 steps. When H goes from here, the H plus that has gone from here, it will react with FeBr4 minus, and what will form? FeBr3 and HBr. This is the conjugate base. This is the conjugate base of the Lewis acid. It acts as conjugate base of Lewis acid. Therefore, a base is something that can donate a pair of electron. Here the Lewis acid is this thing. So here what happens? It acts as conjugate base of Lewis acid. So it donates the pair of electron and it becomes HBr, and FeBr3 is back as catalyst and is restored. So a catalyst, as you know, it doesn't participate in the reaction. It speeded up the reaction by bringing in dissociation of Br2, Br, right? From one side Br positive was being pulled by benzene ring. From the other side Br negative was being pulled by FeBr3. It speeded up. It catalyzed the reaction. We have seen that. And how it came back also we have seen through acid base reaction, conjugate acid base reaction. So this is what the bromination of nitrobenzene is. Dear students, I hope you liked and understood the class. If you have found it beneficial, please do not forget to subscribe the channel. That would be a very big encouragement for me. Please do share it and like it. Thank you very much.